Hello everyone, me Kuntal and my partner Ajinkya are going to present our project on symbolic music generation using Pop 909. The goal is to generate pop style piano music as a sequence of musical event tokens instead of raw audio waveforms. We explore two settings, free generation and chord condition generation. The first asks the model to generate music with no external guidance. The second gives the model a melody and chord progression and asks it to generate piano accompaniment. We split the work into two tasks because music generation can be done at different levels of control. In task 1, the model receives no chord labels or melody guidance. It learns from Pop 909 training songs and then generates new music from that learned distribution. In task 2, the model receives a melody and chord progression as input and has to generate piano accompaniment that fits both. This is harder because the output must follow a given harmonic structure, not just sound musical. We compare each trained model against three baselines: random sampling, a Markov chain, and an AMT zero shot control, which is basically a pre-trained model. So the contribution of POP 901 specific training is clearly isolated. We use this data set, which contains 909 pop songs in MIDI format. Each song has three tracks: melody, bridge, and piano. For task 2, the beat level chord annotations are essential. Each chord has both a root note and a quality. We used a fixed split, that is 800 training samples, 55 validation samples, and 54 test samples. Every baseline and trained model is scored on the same held out test set, so all comparisons stay consistent. In the code, you can see that the loader returns one Pop 909 song with melody, bridge, chords, beats, and tempo ready to feed into the tokenizer or the evaluators. Now, coming to tokenization, before training, we convert MIDI nodes into tokens using the anticipatory music transformer tokenizer. Each node becomes three tokens: time, duration, pitch. The time token says when the node starts, duration says how long it lasts, and pitch encodes both the MIDI node number and the instrument channel. So the model can tell whether a node belongs to melody, chord control, or accompaniment. Time and duration are in 10 millisecond units. There are two modes. Task 1 uses an auto-regress token. The model generates freely from past context. Task 2 uses an anticipate token. Melody and chord controls arrive 5 seconds ahead of the target notes, giving the model future musical context to plan against. Now, coming to task 1, which is unconditional generation, symbolic unconditional generation. For task 1, we compare against three baselines. The random sampler chooses pitches uniformly between C2 and C6 and samples durations from a fixed distribution. No musical knowledge gives us a floor. Basically, there is no musical knowledge, so this gives us a floor. The Markov chain baseline learns pitch transitions from Pop 909 training songs and samples note durations from real Pop 909 data. So its rhythm is more realistic than random. Then we also have another baseline called AMT zero shot baseline, which uses a lack pre-trained anticipatory music transformer without any Pop 909 fine tuning. This is our control, which tells us whether broad symbolic musical pre-training alone is enough or whether training specifically on Pop 909 adds something on top. Now, coming to our model, our task 1 model is POP GPT. We call it POP GPT, a GPT-2 style transformer trained from scratch on POP 909. Importantly, POP GPT is not an anticipatory music transformer. The only thing it shares with AMT is the only tokenizer. The architecture is plain GPT-2 and the objective is standard autoregressive next token prediction. POP GPT has 47 million parameters, which contains 6 layers, eight attention heads, 512 dimensional embeddings, 1024 context window. We can see we have this this particular config mentioned here, which is configurable. So if we want to increase the parameters or increase the attention heads, we can always go back and experiment and see which fits our use case best. For task one, we strip the chord track from the input, so the model only ever sees the AR mode prefix and merged melody, bridge, piano, stream. This slide gives the interpretation for the training curve. The best validation perplexity was at step 3500. After that point, validation perplexity began climbing, overfitting. The important detail is that the overfitting lived almost entirely in the time token, not the node token. Like if we see here, the best validation perplexity was at step 3500, something around here. And after that point, it began climbing and overfitting. On the left graph, there are like four perplexity curves. Blue is the overall validation, red is time, orange is duration, green is note. The blue and red curves bend upwards after step 3500. Green, the note perplexity sits flat around 10 throughout. It is not increasing or decreasing. On the right, training loss decreases smoothly. This blue curve is the training loss and decreases smoothly, and the learning rate follows the cosine scheduler. Optimization itself was very stable. What failed was generalization on the time dimension. Now coming to task one results, to answer the question, how well did the model learn? The Now the headline likelihood result. GPT achieved an event perplexity of 50.34. AMT zero shot, the baseline, achieved 336.42. That is like 6.7 times reduction. Pop GPT assigns far higher probability to real Pop 909 music than the LAC pre-trained model does. AMT Zero Shot already had brought symbolic musical pre-training, but it was never shown Pop 909. Pop GPT was trained directly on Pop 909, so it learned the distribution much better. This number comes from the script run likelihood, which course held out pop 909 test clips token by token. So it's a held out test set likelihood result, not a subjective listening claim. But we also need to see the distributional quality. Likelihood isn't everything. We also need to check whether the generated music looks like pop 909. So Pop GPT does very well on harmonic metrics. Pitch class entropy matches Pop 909 almost exactly, which is like 3.36 versus 3.39. So does the number of unique pitch classes, 9.94 versus 10.06, and scale consistency as well, which is around 87% for both. The model clearly learned Pop 909's harmonic vocabulary. The weakness is density. Pop GPT generates about 50% more notes per second than Pop 909, with shorter gaps between them. This is because we trained on the merge melody plus bridge plus piano stream, which is naturally denser than a single melody line. Marco beats us on Pratchett music distance, FMD 192, which is like 192 versus 346, because it samples directly from Pop 909's pitch and duration marginals. So its embedding is hard to beat. That's an honest limitation of our model, not the metric.
Thank you, Guntal. That was a really nice presentation. Hi everyone, I am Ajinkya. I'll be explaining the task 1 summary and I'll be continuing from here onwards. Uh, so, POP-GPT clearly improved the likelihood compared to the zero-shot AMT. It learned the POP 901 pitch patterns very well as the harmonic structures. The model's main weakness was that it generated music which was too dense. So this likely comes from training on a merged melody, bridge, and a piano tracks. So just to sum up, the overall task 1 worked very well for musical structure, but the rhythm and density needed refinement. Moving forward, how did we evaluated it across both the tasks? So we chose likelihood. We used likelihood, which is basically likelihood metrics such as bits per second, event perplexity, and per token perplexity for time, duration, and note. Also, we also use the distribution models across all the models, which included, let's say, the pitch diversity, pitch range, groove density, and the scale consistency. For task 2, we also measured the chord tone accuracy. The freshet music distance compares the generated clips to the POP 909 using the pre-trained music encoder. All the models were evaluated using the 50 generated samples of 15 seconds each. So these metrics together tell us how well the model predicts the real music and how similar and musical generations there are. Moving forward to the condition generation or the chord condition generation. This was the task 2 that was given to us. The task 2 uses the melody and the chord progression as an input. The random baseline forces the 75% of the notes to be the chord tones. So there were basically we basically compared three baseline approaches for the chord condition model melody generation, which was random baseline, the chord condition Markov model, as well as the AMT zero shot. The AMT zero shot receives the chord controls, but without the POP 909 fine tuning, it will mostly fail to use them very effectively. So this was one of the first problems that we had during the processing of the task 2, which was the condition generation. Our first attempt, the fine-tuned AMT only for free generation. So during interference, we added chord controls that the model had not seen during the training. This caused a failure mode called the base collapse. The model started normally, very normally, but then shifted to a sustained low bass notes when the chord controls appeared. So if you could see, this is how it was before collapse and this is how it was after collapse. So we could see these notes in here. And the phase 2 fixes, the phase 2, which I'll be discussing after this, fixes this training model with melody and the chords which are being added exactly from the beginning. So our model, which is a lead sheet fine tuning model, which is the phase 2. So we start from the lac pre-trained AMT. We give the inputs, let's say the melody on the program 56, the chords on program 48. We have a target on program 0. The loss is computed only on the accompaniment tokens. A 5-second look ahead gives the future melody and as well as the chord context. And the learning rate is at IE raised to -5 and the B float values, and we are using 2 GPUs. Again, the most important part in this slide is that the loss is computed only on the accompaniment tokens. So the model learns to generate the missing piano part very easily. This was our fix for the phase 1 problem that caused the base collapse. Moving forward, the lead sheet training curve, the conditional perplexity measures how well the model predicts an accompaniment from melody and chords. So it dropped from 19.86 to 5.87 over 3000 training steps. If we see the code in here, this was the lead sheet training curve. As I mentioned, it dropped from 19.86 to 5.87 over 3000 learning steps. And going down towards the code, if you could see here, it is a very smooth curve and there are no abrupt elements popping around. Training was smooth with no major instability and there was no overfitting as well. This is a graph which shows the perplexity validation, basically the perplexity versus the training steps tuned on the overall AR, time, duration, note, and the lead sheet conditional model. This is the training loss versus the LR schedule, which is the train loss versus the training step from our model that we had built. This is the task 2 results, which basically give us the chord fidelity. The chord tone accuracy measures how often the generated notes fit the active chords. Our lead sheet model scored 0.51 below the Pop 901 melody reference for 0.66. If you could see here, it's 0.79, 0.62, 0.61, and 0.51, and the Pop melody had a reference of 0.66. So the better step next is to compare against the Pop 99 accompaniment instead of the melody. The task 2 results, basically the distributional quality as well as the likelihood, are basically very strong, because the lead sheet model, which is our model, achieved very strong scale consistency at 0.97. The groove consistency also moved closer to the pop reference. If you could see here, the groove consistency improved towards the reference lines, which is a very good sign. The main result is the conditional perplexity of 5.87, which shows the strong learning rate under the chord and the melody guidance. Summing up everything, this is the task. This is the summary for the entire task 2. Basically, we in the phase 2 of the task 2, we removed the bass collapse that was seen. The model followed a very key, and the scales very perfectly. The chord tone accuracy looks low only because we compared the dense accompaniment to the sparse melody. One more thing, which is that the main remaining issue is not the evaluation mismatch, but it is not a model failure, but an evaluation mismatch that we can see in here. So firstly, we have a lead sheet, we model it, we have a chord guided accompaniment, we improve the fidelity, and we perform further improvements. That's it. Thank you, everyone. Before going, I would like to show the few notes that I was talking about in my previous slides, which is basically how the remaining issue is the evaluation mismatch. Hi everyone. So as mentioned earlier, I'll be playing the entire audio clips, starting with the task 1 audio. The task 1 second audio. And this is how the task 2 audio files look like. And we can clearly see the improvement in the task 2. That's it. Thank you.